What if I told you that Python has a secret weapon that can make your code cleaner, faster, and more Pythonic? Let's explore Python's collections module, one of the most underrated gems in the standard library. If you're looking to write more efficient, readable, and professional Python code, this video is for you. Stick around because we will cover practical use cases with real code examples that will completely change how you write your Python code. Let's jump right in. Our first stop is counter. Think of it as a supercharged dictionary that's designed specifically for counting things. Let me show you why this is so powerful. This code demonstrates how to count character frequencies in a string using two different methods. The first method uses a traditional for loop and a dictionary, manually checking if a character exists as a key and then incrementing its value or initializing it to 1. This approach is verbose and prone to errors. The second, more efficient method uses the collections.counter class, which automatically handles the counting of iterable elements. See how much cleaner that is? But counter gets even better. Here we are using advanced features of the counter class, such as the most common method for finding the most frequent elements and counter arithmetic operations. These operations include addition to combine counts, subtraction to remove elements from a count, and intersection to find the minimum of corresponding counts. Okay, let's look at the practical application of the collections.counter class for analyzing web server logs. It begins with a list of log entries where each string contains information about a web request. To analyze the frequency of different HTTP status codes, the code first uses a list comprehension to extract the last element, the status code, from each log entry. This list of status codes is then passed to the counter class, which efficiently counts the occurrences of each unique code. Finally, the code iterates through the status counter using the most common method, printing each status code and its corresponding count in descending order of frequency. This provides a clear, concise summary of the most common responses from the server. This is incredibly useful for data analysis, log processing, and anywhere you need to count occurrences. Next is default dictionary. It is a special dictionary that automatically creates a default value for any key that doesn't exist, eliminating the need for if-else checks. How many times have you written code like this and got frustrated with key errors? Here, we use a standard dictionary and a for loop. It's verbose because it requires an if statement to check if a key, the grade, already exists in the dictionary before appending the student's name to the corresponding list. With default dictionary, this becomes effortless. Here, we are using a default dictionary from the collections module. By initializing default dictionary with list, you're telling it to automatically create an empty list for any new key you try to access. This eliminates the need for the if statement, making the code much cleaner and less prone to errors. Now let's see how defaultDict can be used with different default factories to handle various data types automatically. Here, we initialize several defaultDict instances, each with a different callable object: list for creating empty lists, ent for creating 0, set for created empty sets, and a lambda function for creating a custom default value like NA. Here, we are using defaultDict int to count word frequencies in a string. By iterating through the words and simply incrementing the count for each word, the code leverages defaultDict to automatically initialize the count to 0 for any new word it encounters, resulting in a concise and efficient word counter. Let's look at the practical use of defaultDict to efficiently process and organize e-commerce order data. It starts with a list of dictionaries where each dictionary represents an order. The code then initializes two defaultDict objects: orders by category with a default factory of list, and revenue by category with a default factory of float. By looping through the orders, it groups them into lists based on their category, and simultaneously calculates the total revenue for each category. This is accomplished without needing to manually check if the keys exist, as the defaultDict automatically creates an empty list or a 0.0 float for new categories, respectively, making the code clean and concise. Tired of accessing tuple elements by index? namedtuple is your solution. This code illustrates a powerful way to improve code readability and maintainability by using namedtuple from the collections module. First, it shows a common problem with regular tuples. Accessing elements by a numerical index, such as person tuple 0, is confusing because it's not immediately obvious what each index represents. And here, we introduced namedtuple by creating a new person type with clearly defined field names like name, age, and job. This allows you to access elements using a descriptive attribute, for example, john.name, making the code self-documenting and much easier to understand compared to using numeric indices. Let me show you how namedtuple objects are similar to regular tuples in that they are immutable, meaning their values cannot be changed after creation. An attempt to reassign p1.x equals 5 would result in an attribution error. However, namedtuple enhances the standard tuple with additional useful methods. For example, the asDict method converts the named tuple into a dictionary, while the replace method provides a way to update the object by returning a new named tuple with specified fields replaced. Lastly, we highlight the memory efficiency of namedtuple compared to a regular class instance, which is due to its underlying use of slots to prevent the creation of instance dictionaries. We first create a simple class on the fly called regular class with two attributes, x and y. It then uses sys.getSizeOf to measure the memory usage of an instance of this regular class, and compares it to the size of a namedtuple instance, p1, containing x and y attributes. The output of this code will show that the namedtuple instance is significantly smaller in size. This is because namedtuple uses a memory-efficient slots mechanism which prevents the creation of an instance dictionary, a feature that standard Python classes use and that adds to their memory footprint. Now let's look at a practical use of namedtuple to manage database configurations in a clear and organized manner. Here we define a database config namedtuple with 5 fields: host, port, username, database, and SSL enabled. A dev-config object is created with development-specific settings. A production configuration, prod_config, is then efficiently generated by using the replace method on dev_config, which creates a new namedtuple instance while only changing the values that are different for the production environment. Finally, a connect-to-database function is defined to show how these named tuples can be passed around as arguments, allowing for easy access to the configuration details using their clear field names. When you need efficient operations at both ends of a sequence, deque is unbeatable. There is a significant performance difference between a Python list and a deque, double-ended queue, when adding elements to the beginning of a sequence. It first initializes a list and inserts 100,000 elements at index 0 using lst.insert. This is an inefficient, on the order of n operation for lists, as all existing elements have to be shifted one position to the right. But the same operation with a deque using deque.appendLeft is a highly efficient, on the order of 1 operation. By measuring and comparing the execution times of both methods, the code clearly shows that deque is orders of magnitude for this task, highlighting its suitability for operations that involve frequent additions or removals from either end of a sequence. Now let's look at the key methods of a deque. First, we are initializing a deque with 5 elements. Then we are adding an element to the right using append and to the left using appendLeft. Similarly, it removes elements from both ends with pop and pop_left. The final part of the code illustrates a unique and efficient feature of deque, its ability to rotate elements. The rotate_n method shifts the elements to the right by n positions, while rotate-n shifts them to the left, which is useful for creating circular data structures. Here is a real-world example of using a deque to efficiently find the maximum value within each sliding window of a given size k. The sliding window maximum function iterates through the input nums array while maintaining a deque that stores the indices of elements. This deque is specifically designed to be monotonically decreasing, meaning the elements at the front are always the largest. As the window slides, the code removes indices that are no longer within the current window and removes indices of elements that are smaller than the new element being added. This ensures that the element at the front of the deque, deque0, is always the index of the maximum value in the current window. Once the window is complete, meaning when I greater than or equal to k-1, the maximum value is appended to the result list. This approach allows the problem to be solved in a time-efficient manner, specifically on the order of n, where n is the length of the input array. Ever needed to search through multiple dictionaries in priority order? ChainMap is perfect for this. This code demonstrates how to use the ChainMap class from the Collections module to combine multiple dictionaries into a single logical view. It sets up 3 dictionaries representing different configuration sources: user config, system config, and defaults. These are then chained together using ChainMap, with the order of the dictionaries determining their priority. When you access a key in the ChainMap object, like config debug, it searches through the dictionaries in the order they were provided, returning the value from the first dictionary where the key is found. This makes it a clean and efficient way to handle tiered configurations, ensuring that user settings override system settings, which in turn override the default values. Here are some advanced features of ChainMap, a class used to create a unified view of multiple dictionaries. First, we print config.maps, which reveals the underlying list of dictionaries that the ChainMap is composed of. Next, it introduces the new child method, which creates a new ChainMap by adding a new dictionary, runtime config, at the beginning of the chain, giving it the highest priority. Finally, the code shows how to iterate through all the keys in the combined full config object, accessing the values that are resolved by checking each dictionary in the chain until a match is found. This provides a clear and concise way to manage hierarchical settings and configurations. Let's look at a practical use of ChainMap to manage hierarchical application configurations from multiple sources. It simulates 4 different sources of configuration data: command line arguments, envvars, a configuration file, and a set of defaults. These are combined into a single ChainMap object called appconfig, with the order establishing a clear priority. Command line arguments override environment variables, which override settings from a config file, and finally, defaults provide fallback values. The start server function then accesses these settings through the appconfig object, which automatically resolves each key to the value from the highest priority source that contains it, resulting in a flexible and robust configuration system. Before Python 3.7, regular dictionaries didn't preserve insertion order. OrderedDict was the solution, and it still has unique benefits. Here in this code, we can see the key difference between a standard dictionary and an OrderedDict from the Collections module. Before Python 3.7, regular dictionaries did not guarantee that the order of keys would be preserved, which could lead to unexpected behavior. In contrast, OrderedDict was specifically designed to always remember and maintain the order in which its keys were first inserted. While modern Python 3.7 Plus dictionaries now also preserve insertion order by default, OrderedDict remains useful for situations where a clear and explicit guarantee of order is critical, or for maintaining compatibility with older versions of Python. Here are several unique and powerful features of the OrderedDict class that go beyond simple order preservation. First, we initialize an OrderedDict and then uses the move-to-end method to reorder elements. Calling move-to-end without last argument moves a key to the end of the dictionary, while move-to-end with last equals false moves it to the beginning. Also, we are showing how pop_item can be used to remove elements from either end of the dictionary. When called with last equals true, it performs a LIFO, last in first out operation, removing the most recently added item. Conversely, when called with last equals false, it performs a FIFO, first in first out operation, removing the oldest item, effectively allowing the OrderedDict to function as a stack or a queue. Here is a real-world example, a classic implementation of a least recently used LRU cache using OrderedDict. The LRU cache class initializes an OrderedDict and a fixed capacity. The get method retrieves a key's value and, if found, uses move-to-end to promote it to the most recently used position. The put method adds a new key value pair or updates an existing one, also moving it to the end. The core logic for LRU eviction happens here. If the cache is at capacity and a new item is added, pop_item last equals false is used to efficiently remove the least recently used item, the first one in the OrderedDict. This elegant use of OrderedDict's ordered and efficient move-to-end and pop-item methods allows for a highly performant LRU cache implementation. Want to create your own custom containers? These base classes make it incredibly easy. First is UserDict. This example shows how to use UserDict to create a custom dictionary-like class called SmartDict. Unlike inheriting directly from dict, which can be complex, inheriting from UserDict provides a cleaner, safer way to customize a dictionary's behavior. The SmartDict class overrides three key methods: setItem for setting values, getItem for getting values, and contains for checking membership. In each of these methods, it automatically converts string keys to lowercase before interacting with the underlying dictionary, which is stored in self.data. This allows the SmartDict to handle keys case-insensitively, as shown by accessing name and age with various capitalizations and successfully finding them. Next is UserList. This example shows how to extend the functionality of a list by creating a custom class numberList that inherits from collections.userList. Unlike inheriting directly from list, using UserList provides a safe and easy way to build on a standard list's behavior. The numberList class ensures that only numerical types, integers and floats, can be added. It achieves this by overriding methods like setItem, append, insert, and extend to include a validation step with a private helper method, validateNumber. This method raises a value error if a non-numeric value is provided. The class also adds new custom methods, sum and average, which operate on the list's data, showcasing how UserList allows for both validation and the addition of new features. Now let's explore UserString, a hidden gem that lets you create custom string classes with additional functionality. The example demonstrates why inheriting from UserString is a more robust and reliable approach for creating custom string classes compared to subclassing str directly. The traditional method of subclassing str requires you to override methods like new and eq, but it fails to ensure that standard string methods, such as upper, return an instance of your custom class. This means the custom behavior is lost as soon as you call a built-in method. In contrast, inheriting from UserString provides a cleaner solution. It stores the string data in the self.data attribute, and its methods are designed to return instances of the subclass, as shown by s2 equals s1.upper, returning a case-insensitive string object. This makes it easier to create subclasses that maintain their custom behavior across all string operations. The Collections module has some hidden gems for very specific scenarios. Let me show you the most useful ones. MutableMapping. We can use it to create custom mappings. This code demonstrates how to create a custom dictionary-like class, FileDict, that inherits from the abstract base class MutableMapping. This inheritance ensures the class behaves exactly like a standard dictionary while also providing a framework to implement core dictionary methods. The FileDict is designed to be a persistent dictionary, automatically saving its contents to a JSON file on every modification. It overrides the setItem and delItem methods to call a private save method, which writes the dictionary's internal data to the specified file. The init method loads existing data from the file if it exists. By implementing the required methods from MutableMapping, this custom class offers a seamless dictionary interface with the added functionality of automatic file persistence. Let's look at the practical example. Here, we use UserDict to create an advanced configuration manager class, ConfigManager, that extends the functionality of a standard dictionary. This class adds powerful features like nested access using dot notation, allowing you to easily retrieve or set values deep within nested dictionaries. It also includes a mechanism for data validation by letting you register custom functions for specific keys. When a value is assigned to a key, the setItem method automatically checks for a validator and raises a value error if the validation fails. This combination of features makes ConfigManager a robust tool for handling complex, hierarchical configurations in a structured and safe way. Here, first, we initialize a config object with a nested dictionary representing application settings. We then add a validation function for the API.rateLimit key, ensuring that its value is always a positive integer. Here, we can see how to access nested values using dot notation with the getNested method, which is much cleaner than using multiple dictionary lookups. Similarly, the setNested method allows for easy modification of deep values. Finally, we use the validation feature by attempting to set API.rateLimit to a negative value, which correctly raises a value error as defined by the validator, preventing invalid data from being stored. Next is MutableSet. The traditional way to build a custom set with extra functionality is to subclass the built-in set type. While this works, it can sometimes be tricky to get right. By using MutableSet, we get a clear contract of what methods we need to implement. Here, we can see the code of using collections.abc.MutableSet to create a custom set-like class, loggingSet, over using a regular set. While a standard set has fixed behavior for operations like add and remove, inheriting from MutableSet provides a structured way to build a class that behaves like a set while allowing for custom logic. By implementing the core abstract methods, add, discard, contains, iter, and len, the logging set automatically gains all the other set methods, such as remove. This is shown when the code calls logs.remove, which is not explicitly defined in the class, but works because it internally calls discard. The custom implementation adds an additional feature. It logs every addition and removal, showcasing how ABCs both provide a clear contract and inherited functionality for creating specialized data structures. Similar to MutableSet, MutableSequence provides a solid foundation for creating custom list-like objects. In this code, we can see a custom list-like container called boundedList that inherits from collections.abc.MutableSequence to enforce a maximum size. By implementing the required methods, getItem, setItem, delItem, len, and insert, the class automatically gains all the other list-like behaviors, like append and extend, which are built on these base methods. The custom logic in the insert method checks if the list has reached its max size before adding an item, preventing overflow. This demonstrates how ABCs provide a clear structure for creating custom data types with built-in constraints while still benefiting from the rich functionality of the standard container they emulate. We've covered 8 incredible ways to use Python's collections module, from simple counting with counter to building complex systems with multiple specialized containers. Before we wrap up, here are my top 3 tips for using collections effectively. The collections module is one of Python's best-kept secrets, and now you have the knowledge to use it like a pro. These techniques will make your code cleaner, faster, and more Pythonic. Drop a comment below with your favorite collections use case. I'd love to hear how you're using these in your own projects.